All right, in this video, we are going to begin chapter 8 of this class. So we've got 3 sections that I need to cover in this chapter. The first one we're going to do today is section 8.1, which is titled arc length. So we're going to talk about how to find the length of different functions using integration to help us. So in this section, there's only one big formula that we have to learn, but it's going to depend on which type of function that you're being given here. So if you want to find the length of an arc, there are 2 variations to the formula. So to find the length of a curve, we will integrate from a to b the square root of 1 plus the derivative of the function squared. So we're going to integrate from a to b of the square root of 1 plus f prime of x squared. And this is the formula that you would use if you are given just a regular y equals f of x function. Now, the good news about this formula is that if you were to do an x equals f of y function, the formula doesn't change at all. So down here at the very bottom, all you would have to do is you would adjust, and instead of doing f prime of x, we could call it something like g prime of y. So the formulas are exactly the same. It just depends on which function variable you're going to be using here. So whether we do an x function or a y function, we will find the length of a curve the exact same way. Now, I traditionally use the f prime of x and g prime of y, but just note that instead of f prime of x, if you want to use dy dx, you can, or instead of g prime of y, if you would like to use dx dy, those are Leibniz notation, and that's perfectly fine. But I traditionally stick to the 2 that are in the purple boxes here. So that's the only thing we're covering in this section. So let's work about 5 problems to show you how to find the exact length of these curves. All right, so example number 1. If y equals 2/3 x to the 3/2, what is the length of this curve on the interval 0 to 2? Now, since this is a y equals f of x function, we are going to end up doing the integral from a to b of the square root of 1 plus f prime of x all squared and integrate that with respect to x. Now, the only thing that we're not given here that you'll have to use is you will have to figure out what your y prime is. Just remember that y prime and f prime are exactly the same thing. So if I take the derivative of this, you would actually just end up with, let's see, x to the 1/2 power. I'm going to plug that along with my parameters into my formula, and I can say that the length of this curve is the integral from 0 to 2 of the square root of 1 plus x to the 1/2 squared dx. When you square x to the 1/2, you will have the integral from 0 to 2 of the square root of 1 plus x dx. And then this should end up being some kind of integration technique that we have probably covered before. This is actually an example of u substitution. So I would let u equal 1 plus x, and therefore du would equal dx. I will have to change my parameters in the process. So if I plug the 0 and the 2 in for x, my new parameter should be from 1 to 3. This will then become the square root of u times du, which is the same thing as the integral from 1 to 3 of u to the 1/2 du. So do your integration technique, and that would be u to the 3/2 with a 2/3 out front that we're going to evaluate from 1 to 3. That means you will have 2/3 times 3 to the 3/2 minus 1 to the 3/2. Now, 3 to the 3/2 is not a perfect number, so I'm not going to be really worried about it. I'm actually going to leave it alone. So 3 to the 3/2. But 1 to the 3/2 is 1, so I will simplify that part, and that is the exact length of your curve. So once again, the formula by itself is not very difficult. You'll have to just apply your derivative to your length of a curve formula, and then the other problems we will figure out how would you go about integrating some of these functions. All right, how about example number 2? if y is equal to x cubed over 3 plus 1 over 4x, what is the length of this curve on the interval 1 to 2? Just like the previous example, this is a y equals f of x function, so we will have to take the derivative of this before we can find the length of this curve. So what I'm actually going to do over here on the right is, if I were to rewrite this function, that would be 1/3 x cubed plus 1/4 x to the negative 1. Because I need to apply the power rule here to find the derivative. That means that y prime would be equal to x squared minus 1/4 x to the negative 2, which is the exact same. Actually, we'll leave it like that. That's actually fine. We'll leave it just like that. So now when it comes to my length of a curve formula, I'm going to end up integrating from 1 to 2, the square root of 1 plus, and I'm going to take my derivative, which is x squared, minus 1/4 x to the negative 2, and we need to square that entire thing. Now, you can square this inside of the square root if you would like, but what I would probably do if I was you is I would come over here to the right, kind of out of the way. Oops, sorry. And why don't we just multiply it by itself to begin with? So if I do my FOIL technique, this would give you x to the 4th minus 1/4 minus 1/4 plus 1 over 16 x to the negative 4. And I'm going to substitute that in after I combine my constants. So that would be x to the 4th minus a half plus 1 over 16 x to the negative 4. So rewriting my integral, we will integrate from 1 to 2, the square root of 1 plus x to the 4th minus 1/2 plus 1 over 16 x to the negative 4 with respect to x. I can then put my constants together, and this would be the integral from 1 to 2 of the square root of x to the 4th. Now it becomes positive 1/2 plus 1 over 16 x to the negative 4. Now, in this example, the way it sits is not able to be integrated. So our ultimate goal now is that since the square root did not go away, we saw the last problem was a nice simple u sub. This one's not going to be a simple u sub because if you let the inside be u, it's not going to come out very nice when you try to find your du. So the only other technique we have here is to get rid of this square root. We are going to have to figure out how to factor the inside of this equation. So using your factoring skills that you learned in algebra, this would end up being the square root of, and you should be able to factor this into x squared plus 1/4 x to the negative 2 all squared, and integrate with respect to x. Once you factor it into this form, the square root and the squared will cancel each other, and we will integrate from 1 to 2 x squared plus 1/4 x to the negative 2nd. And now you've taken a really ugly integral and made it to something a little bit more reasonable here. So this would end up integrating into x cubed over 3. And then if you add 1 to negative 2 and divide by a negative 1, that is minus 1/4 x to the negative 1, evaluated from 1 to 2, which will be a little easier to evaluate if we rewrite it as x cubed over 3 minus 1 over 4x. All right, so plug your upper parameter in. If you plug in 2, that's going to be 8/3 minus 1/8 minus, and then if you plug 1 in, that's 1/3 minus 1/4. So let's see, that ends up becoming 8/3 minus 1/8 minus 1/3 plus 1/4. I can put the thirds together, which gives me 7/3 minus 1/8 plus a 4th. I will need to find a common denominator. So 3, 8, and 4 all go into 24. So let's get all these as common denominators. That would end up being 56 over 24 minus 3 over 24 plus 6 over 24. And when you put all of those numbers together, 56 minus 3 is 53, and 53 plus 6 is 59 over 24. And that is the exact length of this function on the interval 1 to 2. So unlike number 1, where the integration came out really, really nice, occasionally the integration will be a little bit trickier and you'll have a lot more fractions involved. But remember, you just need to go back and cover all the techniques of integration that we've done so far. All right, example number 3. Let's bring in some trig. Find the exact length of the curve y equals the natural log of cosine x on the interval 0 to pi over 3. Once again, this is a function of x, so the first thing I'm going to need to do is find the derivative of this so that I can plug it into my formula. So over here on the right, the derivative of the natural log of cosine would be, you would put a cosine on the bottom, which is the inside, and the derivative of that would go on top. Well, the derivative of cosine is negative sine of x. That now becomes an identity, and we can substitute that as being negative tangent of x. That is what I will plug into my length of a curve formula. So when I set up that formula, we will integrate from 0 to pi over 3 of the square root of 1 plus, and I'm going to take negative tangent of x, square that, and we'll integrate this with respect to x. This is the integral from 0 to pi over 3 of the square root of 1 plus tangent squared of x. Now, while that is not directly a u sub, it actually is an identity that you probably covered in a trig class or maybe reviewed a little bit in Cal 1. This would be the integral from 0 to pi over 3, and 1 plus tangent squared is the exact same thing as secant squared of x. Now you can take the square root very nicely, and you end up with having to integrate a secant function between 0 and pi over 3. Now, secant is not one of the 6 basic integrals we covered early on in this class, but it is one of the rules that was on that chart I showed y'all back in 7.1. This is where you have to know your rules. The integral of secant is actually the natural log of secant x plus tangent x, and I'm going to evaluate that from 0 to pi over 3. So plugging pi over 3 in, you will get the natural log of secant pi over 3 plus tangent pi over 3. And then I will subtract from that the natural log of secant of 0 plus tangent of 0. All right, so this will become the natural log of, let's see, cosine of pi over 3 is a half. And so if you flip that over to get secant, that would be 2. And then tangent pi over 3 is root 3. Minus the natural log of cosine of 0 is 1. So flipping that over keeps you at 1. And then tangent of 0 is 0. Well, that's actually really nice because the natural log of 1, which is what the last piece becomes, that whole thing goes to 0. And you end up with a final answer of the natural log of 2 plus the square root of 3. And that is the exact length of this function here. So while some people do not like trig, trig actually makes some of these problems a lot nicer as long as you know your identities. Not only is regular trig very nice, but actually hyperbolic trig functions are not as bad either as long as you know your identities. So let me show you an example of that. What is the exact length of the curve for y equals 3 plus 1/2 times the hyperbolic cosine of 2x on the interval 0 to 1? Like I said, a lot of these problems we're going to do are going to be y equals f of x functions. So once again, you need to come over here to the right, and we need to find y prime so that I can plug this in. All right, so the derivative of 3 is just 0. So this would be 1/2 times the derivative of hyperbolic cosine is hyperbolic sine of 2x times the derivative of the inside, which is your chain rule, would be 2. So that actually just simplifies into the hyperbolic sine of 2x. Let's plug that into my length of a curve formula. So the length of this curve would be the integral from 0 to 1 of the square root of 1 plus, and if you just square your hyperbolic function, it becomes hyperbolic squared sine of 2x. Now, if you're thinking regular trig functions, you're not going to find a regular trig function that has hyperbolics in it. But if you think back to when we did section 3.11, so in 3.11, there was an identity that said that hyperbolic cosine squared minus hyperbolic sine squared is equal to 1. Now, in my problem, I've got 1 plus a hyperbolic sine squared. So if I were to move that over, I could say that hyperbolic cosine squared of x is equal to 1 plus hyperbolic sine squared of x. The only thing to be aware of in our problem besides that is that we're doing hyperbolic sine squared of 2x. So therefore, we have to use a 2x when we do the identity. So this would be the integral from 0 to 1 of the square root of hyperbolic cosine squared of 2x. But now the square root and the squared cancel each other, and you're just going to integrate from 0 to 1 the hyperbolic cosine of 2x. This can be done by doing the anti-chain rule, which will give you a result of 1/2 the hyperbolic sine of 2x evaluated from 0 to 1, which will give me 1/2 times the hyperbolic sine of 2 minus the hyperbolic sine of 0. Now, hyperbolic sine of 2 does not come out to a very nice number, so we'll just leave it alone. But actually, hyperbolic sine of 0 actually goes to 0. And that's because if you remember back in 3.11, the hyperbolic sine of x is defined as e to the x minus e to the negative x, all divided by 2. And if you were to plug 0 into both of these x's here, you would end up getting 1 minus 1 over 2, which is 0. So that allows you to get rid of that term, and we can say that the final answer is 1/2 the hyperbolic sine of positive 2. So once again, trig comes out really nice, but you will need to know your identities in order for these to work. All right, and then I want to do one more question just because we have not done actually an x equals f of y function, even though it works the exact same way. So let me end this video on doing one more problem. If x is equal to 1/3 root y times y minus 3, what is the exact length of this curve between 1 and 9? Now, unlike the other ones where we just found the derivatives, this one might take a little bit of rewriting. So what I'm going to do is I'm going to write this as x equals 1/3 y to the 1/2, and I'm going to actually distribute both of those terms through to the parentheses. This would allow me to say that this is 1/3 y to the 3/2 minus y to the 1/2. I can now find x prime, just like we found y prime on the previous 4 problems. So the derivative of this would actually be 1/2 y to the 1/2 minus 1/2 y to the negative 1/2. We are now going to substitute this into our length of a curve formula, which is exactly the same. The only difference is we're going to integrate from 1 to 9 the square root of 1 plus 1/2 y to the 1/2 minus 1/2 y to the negative 1/2 all squared, and we will integrate this with respect to y. Now, this to save a little bit of room here, what I would technically do here is I would take this term and I would FOIL it. I showed y'all how to do that back on example number 2. So if you need to, come over here to the side and do your scratch work. But I'm going to kind of do this to save us some time here. This will be the square root of 1 plus. And when you FOIL this out and combine your like terms, you should get 1/4 y. Then you're going to end up getting a minus 1/2 plus a 1/4 y to the negative 1 dy. You can now put your constants together. So this is the integral from 1 to 9 of the square root of 1/4 y. Now it's plus 1/2 plus 1/4 y to the negative 1. If you look back at example number 2 that we did earlier, we're going to run into the same predicament here, is that this is not going to be a u sub problem because there's not letting the inside be u does not make this simplify very nicely. There is no trig to help us with an identity, so the next instinct is that I need to factor the inside so that the square root will go away. So when you factor the inside of this square root, it should come out to be, let's see, 1/2 y to the 1/2 plus 1/2 y to the negative 1/2 all squared dy. Taking the square root of the squared term now allows me to write this as the integral from 1 to 9 of the, I meant to cancel the square root, don't do that. The square root and the squared cancel, and you just get 1/2 y to the 1/2 plus 1/2 y to the negative 1/2. After all of that, you can finally start integrating this function. So coming back up here, if I integrate both of those terms, this will end up being 1/2 times, that is y to the 3/2 times 2/3, plus 1/2 times, that is y to the 1/2 times 2, and we will evaluate all of that from 1 to 9. Cleaning this up is going to give me a 1/3 y to the 3/2 plus y to the 1/2 evaluated from 1 to 9. Let's plug the 9 in. So that would be 1/3 times 9 to the 3/2 plus 9 to the 1/2 minus 1/3 times 1 to the 3/2 plus 1 to the 1/2. Simplify all these rational exponents, and you should end up getting from left to right. 9 to the 3/2 is actually going to be, let's see, 27, and 27 times 1/3 is 9, plus the square root of 9 is just 3, minus, these ones don't really do much, so it's just going to be a 1/3 plus 1. All right, so that ends up coming out to be 12 minus 1/3 minus 1, which is equal to 11 minus 1/3. And then when you find common denominators there, it should be 33/3 minus 1/3, which gives me an exact length of this curve as being 32/3. So the idea is not any different when you do x equals f of y. You're just going to be doing everything in terms of y instead. So, like I said, in this video, we talked about how to find the exact length of a curve, whether it be y equals f of x or x equals f of y. Make sure you notice these different integration techniques because some similar ones are going to show up in the next video. In the next video, we're going to end up doing surface area of revolutions, which part of that formula is actually going to be length of a curve. This is not the last time we will be doing these formulas, but we've got to add some more stuff to it in order to do surface area. So I'll see you in the next video.